My dear students, in the previous lecture, I have discussed about the transportation problem and the different way to find out the solution of the transportation problem. And the three different techniques we have learned to find out the solution of transportation problem. One is northwest corner method. Second one is matrix minima method. Third one is Vogel's approximation. When we are going to solve the transportation problem, first we have checked whether it is balanced or not. If not, then we introduce dummy origin or dummy destination. Corresponding transportation cost is equals to 0. And then we try to find out the solution by these three techniques. In the previous lecture, I shown you that depending on problem, three different techniques we have used, and we shown you that the Vogel's approximation methods gives you the best result. So whenever nothing is mentioned, we must go for the Vogel's approximation. But whatever the solution we are getting, that is basically the initial basic feasible solution. So whether this initial basic feasible solution is optimum or not, that we are going to discuss today. And the technique we are following here is nothing but the modified distribution method or MODI method. So what are the steps basically I have given here? That first we will find out the solution by the northwest corner method Vogel's approximation method as I. Now, after finding out the solution, we will see that whether it is the number of allocated cells is equals to m plus n minus 1 or if the number of allocated cell is equals to m plus n minus 1, then we will proceed. And in this case, we will get a non-degenerate solution. If the number of allocations is not equals to m plus n minus 1, then another process will follow. Basically, we will use a dummy allocation which basically do not form a loop. So what is loop? I will discuss later on. But initially, we are trying to find out the technique of the MODI method. So after finding out the solution, basically what we are doing, let's parallelly I am going for one problem, then I think it will be more clear to you. Let us choose this problem. So in this problem, you can see that there exists three origin, three destination. The available amounts are given here, and these are the demand of the destinations. And here the problem is balanced. So we are using here Vogel's approximation method to find out the solution. And in this case, you can see that whenever we are using the Vogel's approximation method, then we are getting the initial basic feasible solution as is nothing but this one. So I am not going to discuss Vogel's approximation method now because already it has been discussed in the previous lecture. Now, here you can see that m plus n minus 1. M is nothing but the number of origin. N is the number of destination. So, here the number of allocated cell is equals to 1, 2, 3, 4, 5. And so, this 5 is equals to nothing but 3 plus 3, 3 plus 3 minus 1. So, this condition is satisfied. So, basically, we will get a non-degenerate solution. Okay. Now, what is the technique? Once again, I am going for the technique here. So, what we are doing here, In each origin and each destination, we are defining the dual variable ui and vj, which satisfying the condition ui plus vj is equals to cij for the allocated cells. And you will see here that here the number of variable is m plus n, but the number of equation you will get is nothing but m plus n minus 1. So to find out the all variable value, what we are doing, we have to choose one base variable equals to 0. So what dual variable we choose, we equals to 0 is nothing but the variable corresponding which row or in which column the maximum allocation is there. If there is one or two row with the same number of maximum allocations, then any one you can choose that equals to 0. Okay. So after choosing this, you will be able to find out all UI and all VJ separately. Okay. So when you are able to find out all these values, then we will calculate the cell evaluation or net evaluation or opportunity cost, which is denoted by delta ij and is defined by Cij minus Ui plus B. So the steps 2 I am discussing with the problem 1 second. See here. Already I have shown you that this is the solution we got by the Vogel's approximation method. So the optimality test, you have seen that the number of allocated cell is nothing but m plus n minus 1. So the solution is non-degenerate. Okay. Now we are basically finding out the UV method to find out the optimality test. So you can see here, you in this row maximum allocation is there. So I have chosen U3 is equals to 0. As for allocated cells, Cij is equals to Ui plus Vj. So you can see here these type of relations you will get. So see here, from these, you are getting what? Number one relation you are getting is nothing but for this cell, you can write down U1 plus V2. This is equals to 7. U1 plus V3. U1 plus V3. This is equals to 8. U2 plus V3, this is equals to 9. U3 plus V1, this is equals to 7. And U3 plus V2, this is equals to 8. So these are the 5 equations you are getting. And as you have seen that the maximum allocation in the third row is present. So you have chosen U3 is equals to 0. So when you are putting U3 equals to 0, then you are getting V2 is equals to 8. When you are putting V2 is equals to 0, then using this relation, you are getting U1 equal to minus 1. As U1 equal to minus 1, so using this, you are getting V3 is equals to 9. And then as V3 is equals to 9 already you got. So you are using this relation, you are getting U2 is equals to 0. And then using this and this, you can get V1 is equals to 7. So you are able to find out all these values of UI and V. Now, for the non-allocated cells, as you see that I circled these one. So these are the non-allocated cells, and we are calculating del Ij for the non-allocated cells. Means delta 1, 1, delta 2, 1, delta 2, 2, and delta 3. So you can see here that we have calculated all these values. And here you can see that all these delta Ij are greater than equals to. So that thing basically is written in these steps. That if all the del Ij is greater than 0, then the solution is optimum solution. If one or more unoccupied cells have negative cell evaluation or opportunity cost, then the solution is not optimum and the further process will follow at that time. So basically, in this particular problem, you can see that all del Ij is greater than equals to 0. So the solution is optimum. Means the solution, whatever we got in this step, this one is nothing but our optimum solution. And at that time, the optimum transportation cost will be what? 40 into 7 will get 40 into 7 plus 5 into 8 plus 15 into 9 plus 25 into 7 plus 15 into 8. So that will be your optimum transportation cost, and that we have found here. That the optimum transportation cost is nothing but our 7. So here the observation we have to be clear about that if all delta Ij is greater than 0, the solution is optimum and unique. Be careful. If all delta Ij greater than 0 with at least one delta Ij equals to 0, then the solution is optimum, but not unique. Basically, in this case, there will exist another solution. But if delta Ij is less than 0, then the solution is not optimum. And at that time, we will follow some process to find out the optimum solution. Okay. So today's lecture, basically, we are checking out that how we will find out the optimum solution. But in these cases, whatever the problem today I have chosen, all these cases, you will see that in the first step, you are getting all delta Ij is greater. Okay. So I hope it is clear to everyone. So thank you, everyone. I hope this lecture will help you to find out to check it out, the optimality test of a transportation problem. In the next lecture, we'll go for one problem where you can see that at least one delta Ij is less than 0, and at that time, what technique will follow, that we'll discuss in the next lecture. Thank you. Thank you, everyone.